Imagine waking up in a small village nestled at the base of a smoking mountain. The ground rumbles gently beneath your feet, warm mist seeps through cracks in the earth. The locals say the volcano is quiet, for now, but they always keep one eye on the mountain. Why do people choose to live near active volcanoes? Surprisingly, there are good reasons. The soil is rich for farming. Geothermal heat can power entire towns. And in many places, cultural traditions and histories are deeply tied to the volcanoes themselves. But living there also comes with danger. What happens when the mountain awakens? Volcanoes are more than fiery eruptions seen in movies. They are complex systems that release energy in many ways. Sometimes the danger is visible, like glowing rivers of lava flowing down a slope, but often the threats are invisible. Poisonous gases like sulfur dioxide can seep out quietly. Ash can fill the air, turning day into night. Superheated clouds of gas and debris, called pyroclastic flows, can travel faster than a car, destroying everything in their path. Even the ground itself can crack, rise, or collapse. To survive in these places, we need more than bravery. We need knowledge, science, and smart design. So how can we protect people who live in such extreme environments? One answer is to build better shelters, not just strong ones, but smart ones that understand the volcano's language. For example, scientists have designed buildings made of special materials that can survive intense heat. Some use layers of ceramic or volcanic rock to keep the inside cool, even if the outside is burning hot. Others use advanced insulation made from aerogels, the same kind of material used in space missions. These buildings are more than walls and roofs, they are shields, keeping people safe when temperatures rise to over 1,000 degrees Celsius. But heat is not the only threat. What about the air? Volcanic gases can be deadly if breathed in. Some shelters use high-tech air filters, similar to those in submarines or space stations. They clean the air inside while keeping out the gases outside. Some even have pressure systems to keep ash and smoke from sneaking in through small cracks. And in case of emergency, shelters can be built with underground tunnels or escape pods. Can you imagine a school or hospital with a hidden emergency tunnel built into the mountain? In many high-risk zones, such ideas are already becoming reality. And here is a fascinating twist. Volcanoes are not just dangerous, they are powerful energy sources. In Iceland, for example, entire cities are heated and powered using geothermal energy from volcanic sources. Could we do the same in other places? Could a shelter in a volcano zone use the volcano's heat to generate electricity, purify water, or run medical equipment? The answer is yes, and scientists are working on systems that turn volcanic heat into useful power, even while protecting people from it. You might be wondering, how do we know when a volcano will erupt? That is where science plays a crucial role. Using satellites, drones, and underground sensors, scientists can detect tiny changes in the Earth's surface. They listen to the rumblings inside the volcano, measure gas levels in the air, and track how the ground is moving. With this data, they can often give early warnings before an eruption happens. That extra time, sometimes just hours or days, can save thousands of lives. In the future, AI systems may help predict eruptions even earlier by analyzing patterns that humans might miss. The big question remains, can we not just survive near volcanoes, but live safely and even benefit from them? The answer seems to be yes, if we approach the problem with creativity and science. With better design, smarter monitoring systems, and international cooperation, we can create communities that thrive in harmony with the Earth's most powerful natural forces. Living in a volcano zone does not have to mean living in fear. It can also mean living at the cutting edge of innovation and resilience. Have you ever wondered what it would feel like to stand safely near an erupting volcano, watching the Earth create itself in real time? With the right knowledge and preparation, this vision may one day be part of everyday life in some parts of the world. In learning to live with volcanoes, we may discover new ways to live more wisely with the planet itself. Geothermal hazards in active volcano zones arise from the Earth's internal heat manifesting as lava flows, pyroclastic density currents, hot ash deposits and gas emissions, delivering extreme temperatures, often exceeding 1,000 DGC for lava and 500 DGC for pyroclastic flows, that can rapidly transfer heat by conduction, convection, and radiation over distances of kilometers. Understanding the physical properties of volcanic materials, thermal conductivity, specific heat, emissivity is essential to predict heat exposure levels for structures and people, and accurate hazard mapping relies on integrating geophysical monitoring with thermal modeling to delineate high-risk zones. Thermal imaging during the 2018 Kilauea eruption mapped lava flow temperatures above 1,200 DSC, enabling evacuation of at-risk communities. It's like charting the path of a wildfire by tracking infrared hotspots to stay ahead of rapidly moving flames. Survival in active volcano zones requires mitigating exposure to lethal thermal fluxes, toxic gases, and ground instability while maintaining breathable air and safe shelter. Key survival metrics include maximum allowable heat flux, 10K-2 for 30 minutes, gas concentration thresholds, SO2 less than 1 ppm, and structural integrity under ash load. And effective survival strategies combine engineered refuges, personal protective equipment, and real-time hazard alerts to extend human tolerances long enough for evacuation or until volcanic activity subsides. In Nevado del Ruiz, 1985, inadequate shelter and late warnings led to tragic fatalities from pyroclastic surges. It's like preparing a bunker against a storm of molten debris and poisonous fumes instead of wind and rain. Lava flows emit intense radiant heat that can ignite flammable materials and cause third-degree burns at distances up to 50 mm. Radiant heat flux decreases with the square of distance but remains dangerous in the near field, requiring shelters to withstand greater than 20 kW/m2 for prolonged periods, and reflective and insulating materials minimize heat absorption, while structural orientation reduces direct exposure, with thermal modeling informing minimum setback distances and required insulation thickness. A heat-resultant shelter prototype in Iceland with reflective aluminum cladding survived within 30 m of active lava flow without interior temperature rise above 40 DEC. It's like wearing a firefighter's aluminized suit that reflects a furnace's heat, keeping the wearer cool even when standing near flames. Pyroclastic flows combine scorching gas and volcanic debris traveling greater than 100 m/s at greater than 400 DGC, destroying structures by thermal shock and impact, while ashfall layers impose heavy loads on roofs greater than 500 kg/m2 and reduce air quality, causing respiratory failure without filtration. Shelters must be structurally reinforced and equipped with HEPA filtration for breathable air, and sealed, overpressurized interiors prevent infiltration of hot gases and fine particulates. In Mount St. Helens, 1980, many buildings collapsed under ash loads exceeding 200 minimum depth. It's like trying to live inside a snow globe filled with hot, abrasive dust that suffocates and smothers anything unprotected. Volcanic gases, primarily SO2, CO2, and H2S, supposed acute toxicity risks and exacerbate heat stress by reducing oxygen availability. CO2 can accumulate in low-lying areas, displacing breathable air, while SO2 forms acidic aerosols that corrode materials, so shelters require active gas scrubbing, soda-lime CO2 absorbers, activated carbon filters, continuous gas sensors for alarm trigger, and proper ventilation design to ensure positive interior pressure and block infiltration. The 1986 Lake Nyos disaster released a CO2 cloud that suffocated 1,700 people within minutes. It's like sealing yourself inside a scuba suit that filters out carbon monoxide while surrounded by invisible toxic fumes. Effective shelter materials combine high thermal resistance, ceramic fibers, refractory concretes, with low thermal conductivity, less than 0.05 W/mk, and structural strength under high temperature using multi-layer composites, reflective outer skin, insulating middle layer, and structural core to provide passive protection for hours against greater than 1,000 DFC external heat while resisting acidic corrosion and abrasive ash. Modular panels allow rapid assembly and customization to varied terrains. A shelter prototype using ceramic fiber blankets and stainless steel cladding maintain interior temperatures below 50 DCC when exposed to 800 DC radiant heat for 60 minutes. It's like wearing a layered winter coat. an outer windbreaker, a middle insulating fleece, and an inner moisture-wicking liner to stay comfortable in extreme cold. Volcano shelters integrate structural reinforcement, thermal insulation, and life support systems into compact, deployable units featuring sloped roofs to shed ash, elevated floors to avoid CO2 accumulation, and aerodynamic shapes to deflect pyroclastic surges. Redundant power supports ventilation and sensor networks, while water storage and first aid kits sustain occupants for 48 plus hours, and CFD simulations optimize airflow and heat transfer under eruption scenarios. A Japanese research team developed an inflatable refuge pod that self-erects and seals against ash and gas in under 5 minutes. It's like an emergency lifeboat that pops open instantly and protects occupants from freezing water, except it shields against scorching debris and toxic fumes. Effective survival hinges on rapid detection of volcanic unrest via seismic, infrasound, gas, and thermal sensors networked to alert systems. Real-time data feed hazard models that predict eruption trajectories, timing, and intensity, and automated alerts trigger shelter activation protocols and evacuation routes, while updating occupancy status with IoT integration, ensuring resilient communication even under infrastructure damage. The 2018 Mount Agung eruption warnings in Bali used continuous GPS and gas monitoring to evacuate 100,000 residents before pyroclastic flows arrived. It's like a smart home security system that detects smoke, heat, and gas leaks and automatically locks doors, turns on fans, and calls for help. Emerging advances include self-healing refractory composites, phase change thermal buffers, and AI-driven hazard prediction for adaptive shelter deployment, with biomimetic cooling systems modeled after termite mounds for passive ventilation and 3D printing of shelters using local volcanic ash as aggregate, promising networked micro-refugees across high-risk zones for scalable, community-driven resilience against geothermal hazards. A pilot project in Iceland uses 3D printed volcanic ash concrete to build prototype shelters directly from local materials. It's like planting tiny oases of safety throughout a desert, each automatically springing up from the sand when a sandstorm approaches.